Okay, well, here we are for the second video of the week. Those of you in the Monday section, those of you who were there, hint, hint, uh, have actually seen me work this problem before. We didn't quite get to that in the Wednesday section, and it involves a quadratic equation, so I think the Monday section could use a do-over on it. I mean, just you could stand to see it again. If you were there Monday and you understood it just fine, then you can fast forward a little bit through this example. But this is an example of using our kinematic equations to find some information about a car that's merging onto a highway. This is the kind of stuff that traffic engineers might want to use, and they actually do use equations like this to find out this kind of information. In this case, the ramp is 200 meters long. The initial velocity of the car entering the ramp would be 10 meters per second, and it accelerates at a rate of 2 meters per second squared. So the question would be, how long would it take the car to reach the far end of the ramp? The traffic engineers would want to use an equation like this to basically gauge, how, well, for one thing, how long ramps should be, or how long would it take a car to traverse the length of a ramp if the car is going at a reasonable speed with reasonable acceleration. Because they don't want to build things that require, really outlandish behavior from drivers in order to accomplish things in a reasonable amount of time. So for solving the problem, first it wouldn't hurt to draw a little diagram. So you've got the original position of the car, which the problem didn't really give you any information on what to call the original position of the car. And in cases like that, you might as well just call it 0. And the original velocity at that point in time is 10 meters per second. The car has to traverse a distance of 200 meters. So that's x final, 200 meters. Velocity final, we don't know. And also, we don't know the time that it takes to do that. We do know that between this point and the final point, the acceleration is 2 meters per second. And that's positive because it's going in the same direction. That is, the acceleration is in the same direction as the direction of movement. So the car is going faster and faster in the direction it's traveling. So the things that we know, we can set up the things that were given in the problem, or maybe now what you have to watch out for in some of these cases is sometimes things are not explicitly said in the problem. But if you think about it, you realize that you know it, or you can assign a value to it just based on what the problem said, even if it wasn't named explicitly in the problem. Like, for instance, x original, the original position, the problem didn't actually say anything about that. And in cases like that, you can normally call the original position 0. Okay. And we also know that if the original position is 0, then the final position is 200 meters. You could call actually the original position anything you want because the problem didn't mention it. But whatever value you assign to the original position, you do have to make sure that the final position is 200 meters greater. So if you wanted to say x original is 100 meters, that's fine. But then x final would have to be 300 meters. So that's really the only thing that matters, is the difference between x original and x final. We also know that the original velocity is 10 meters per second, and we don't know the final velocity. We know that the acceleration is 2 meters per second squared, but we don't know the time, how much time it takes. So what we can do is use the equation x final equals x original plus v original t plus 1/2 at squared. Basically, we know everything here except for time. Now, the one little catch, though, is that in most of the examples we've seen using this equation so far, either v original or acceleration will be 0, and that time containing term will drop out, so that you only end up with 1 t in the equation to be unknown. In this case, v original is 10 meters per second. Acceleration is 2 meters per second squared. Both of these t's are going to remain in the equation as unknowns. And that means we're going to be faced with a quadratic equation. All right, so just as a review, because sometimes it's unavoidable, we'll put in the values and set up the equation, and then we'll go through the quadratic equation. So what we've got is x final, that's 200 meters, is x final, equals x original, which is 0 meters, plus v original, which is 10 meters per second, times time, plus 1/2 the acceleration, which is 2 meters per second squared, times time squared. T and t squared are the unknowns. And of course, 0 meters drops out, and you end up with 200 equals 10t minus or plus t squared. And then you rearrange this to get it into the customary form for quadratic equations, which is descending order of the power of the unknown. So we want the t squared term first, and then the t to the first power term, and then the t to the 0 power term, remembering that t to the 0 power is 1, so you don't actually write t to the 0 power. And so when you rearrange this equation to put it in that customary order, you get t squared plus 10t minus 200. And that equals 0. With a quadratic equation, you always want to set it equal to 0. Because we've got t to the second and t to the first and t to the 0, that makes it a quadratic equation. And we can solve it using the customary quadratic equation, which is negative b plus or minus b square root of b squared minus 4ac over 2a. In this case, in the quadratic equation, traditionally a is the coefficient for the squared term, b is the coefficient for the variable to the first power, and c is the coefficient for the variable to the 0 power. So a is 1, b is 10, and c is negative 200. Don't miss the negative sign, it's negative 200. So inserting those values into the quadratic equation, we get negative 10 plus or minus square root of 10 squared minus 4 times 1 times negative 200. If you forget the negative sign here, you're going to end up trying to take the square root of a negative number, and you're going to have a hard time doing that. Okay, and all of that is over 2 times 1. And so we get negative 10 plus or minus the square root of 900 over 2. That's negative 10 plus or minus 30 over 2. 30 is the square root of 900. And that gives us two possible values, as we normally get from the quadratic equation. One of them would be if you take negative 10 plus 30 over 2. Negative 10 plus 30 would be 20, divided by 2 is 10. And negative 10 minus 30 would be minus 40, divided by 2 is negative 20. And normally one of those values will be reasonable given the context of the question, and one of them will not be reasonable. So looking back at the question, what is it we're looking for here? What variable are we solving for? We're solving for t, which is time. Time has to be positive. Time only goes in one direction in real life. So the positive number has to be the answer. 10 seconds is the time. Okay, so time is 10 seconds. The negative 20, not possible because it would mean time is going backwards, and it doesn't do that. Okay, and an extra question might be what you might be wondering, what would be the final velocity of the car be at the end of that ramp? Because you want to say, okay, we've got a ramp of a certain length, we've got a car that approaches at a reasonable speed and with a reasonable rate of acceleration. Could the car be going fast enough to merge with traffic by the end of the ramp? And if it's going too slowly, then you might want to make the ramp longer. And if it's going too fast, you might want to make the ramp a little shorter. So for that, we can use the equation V final is V original plus AT. We've got all of this information except VF, so you just put in the numbers. V original was 10 meters per second. We know from the question that the acceleration is 2 meters per second squared. And now we know that that acceleration goes on for 10 seconds. And that gives you a final velocity of 30 meters per second. And then when you convert that to kilometers per hour or miles per hour, you will find out whether that's a reasonable speed to be entering into a highway. Okay. All right, so that was a little harder than most because it involves the quadratic formula. I usually try to avoid the quadratic formula, but sometimes it's not easy to avoid. Moving on to another example, we have a spaceship leaving Earth's orbit. This is the kind of thing that we have to deal with in physics sometimes because space travel and astronomy are part of physics. And this time they're heading for the moon. Their acceleration is 20 meters per second squared for 2 minutes. And I did you the little favor of reminding you that times need to be in seconds. So 2 minutes is 120 seconds over a distance of 1,000 kilometers. But remember, actually, I didn't convert it here, but remember, distances have to be in meters. So what are the original velocity and the final velocity? This is a fairly difficult example because no one equation is going to give the answer for both of those questions. So first, you're going to have to find an equation that will determine one of those velocities, one or the other, and then use a different equation to find the other velocity. So what we can do first is use the equation that we used up above, and that is final position equals original position plus the original velocity times time plus 1/2 at squared. And what we want to know from this, the only thing there we don't know from this, in fact, is v original. So if you rearrange this equation to solve for v original, you first, just as a review, we can show how this is done. Okay, so if you want to rearrange this equation to solve for v original, first thing you do would be get rid of the terms that are being added on the right-hand side. So you can bring x original over to the other side by subtracting it from both sides. That'll get rid of this. You can also get rid of this by subtracting it from both sides. So minus 1/2 at squared. Subtracting this 1/2 at squared from the right-hand side cancels it out, but you end up with it subtracted on the left-hand side. And that is equal to v original times t. So at that point, all you would have to do is divide both sides by t, and that will get rid of that t. Now you've got v original. And that is, it better be what we came up with. Yeah, so VF, that is, final position minus original position minus 1/2 at squared over t will give you v original. Okay. They're not talking, well, yeah, they're not talking about the spaceship taking off from the launch pad, so you can't just assume that the original velocity is 0. And so that's why we have to find v original. Okay, the final position is 1,000 kilometers from where we start observing, but that has to be in meters. So 1,000 kilometers times 1,000 meters per kilometer gives you 1,000,000, or 10 to the 6th. So that's where I got 10 to the 6th meters. The 6 was originally a little low there, so that's what I scribbled out. Minus the original position, Well, the original position will be the position at which we first start observing the rocket. And so we can consider the original position to be 0. So we'll call that 0 meters. Minus 1/2 AT squared. Well, we know that the acceleration is 20 meters per second squared, and we know that it goes on for 120 seconds. And just be careful that you don't forget that that 120 has to be squared when you work everything out. And then all of that is divided by the time, which is 120 seconds. So when we work this out, 1,000,000 minus nothing minus 1/2 20 times 120 squared, and make sure that it's only the 120 that gets squared, not the whole thing. You end up with, this got a little smudged, but 856,000 meters divided by 120 seconds. Okay. And that works out to 7,133 meters per second. That's the original velocity. For the final velocity, all we need to do is use original velocity plus AT, assuming the acceleration is constant over that time. And the problem didn't explicitly say the acceleration was constant, but it didn't give us any reason to think otherwise. So we can assume that it's constant. So V final would be V original, that's 7,133 meters per second, plus 20 meters per second squared times 120 seconds, or 9,533 meters per second. And again, choosing which equation to use is basically just looking at the list of equations that you have to use, and deciding which question is it that will give me what I want, what do I know, and which basically it's usually a question of which equation is it where I know everything except one thing. And most of the time, that's the one you want to end up using. Okay. The next topic is section, sorry, it's hidden with a staple there, so I can't see, but it's the next section anyway. And it's two-body pursuit problems. These are kind of fun because it involves, things chasing each other or things catching up to each other. So you can have a little fun with problems like this. Two-body pursuit problems are a little more complicated, though, because you've got two objects that are in motion at the same time. And they aren't necessarily in motion in exactly the same way. Very often, one of them will be accelerating and one of them won't, or they'll both be accelerating, but at different rates. And you might want to say, how long does it take one object to pass the other one or to catch up with the other one? And the way you normally handle that is you set up an equation of motion for each of the two objects. And if you're looking for when they catch up to each other, for instance, you take the equation of motion for the two objects and set them equal to each other, and then solve for whatever it is you don't know. Okay, so the motion of the two objects will normally be coupled in some way. Not necessarily coupled literally, but they'll often be coupled in the context of the question, like when does Itchy catch up to Scratchy or that kind of thing. And the unknown sought, like what is the position where they catch up with each other? That will depend on the motion of both of the objects. So you just, like I said, you use the equations of motion for both objects and set them equal to each other and solve them simultaneously. Some examples of this kind of question would be, say, the police catching up to a speeder, or Coyote catching up to a roadrunner, or that sort of thing. Like I said, Itchy catching up to Scratchy, or Tom catching up to Jerry, and on and on and on. Time and so, for example, the time and distance for Wile E. Coyote to catch up to the Roadrunner depends on the original distance between them and their velocities and accelerations, if any. So an actual example of that. So we've got Wile E. Coyote is hiding behind a bush, and he sees the Roadrunner running past at 10 meters per second. At the instant the Roadrunner passes Wile E. Coyote, the coyote accelerates from rest at 4 meters per second squared in order to catch up. Assuming that Wile E. Coyote hasn't slammed into a cactus or gone off a cliff before then, how much time would it take for the Wile E. Coyote to catch up to the Roadrunner? And what is the displacement of the two of them when Wile E. Coyote catches up to the Roadrunner? Okay, so for addressing the problem, we would use the equations for constant acceleration. Wile E. Coyote has an acceleration of 4 meters per second squared, but the Roadrunner is not accelerating. You know that because it says he's running past at 10 meters per second, but it doesn't say anything about the Roadrunner accelerating. And so again, if it's not mentioned, then you're usually safe in assuming that it doesn't exist. So you can assume that that's a constant 10 meters per second, which again means no acceleration. Or in other words, acceleration is 0. You want to set up a separate equation of motion for each animal. You want to find the location. The final location has to be the same for both because we're looking for the moment at which one of them catches up to the other. And whatever that position is, it will be the same for both of them because by definition, if the coyote catches up to the Roadrunner, they must be in the same position at the same time. Okay. The initial locations are also going to be the same, at least in the context of this question, because we're only looking at the chase. So we don't really care how far or how fast the Roadrunner was running before he passed the coyote. We only care about the moment from when the coyote starts chasing him to the moment when he catches up to the Roadrunner. Okay, so the displacements will be the same for both, is what that means. Their initial location is the same and their final location is the same. That means that the change in locations, or in other words, their displacements, must be the same. So you want to use the equation that gives displacement for both, one with constant acceleration, one with constant velocity. But remember, constant velocity is just another way of saying 0 acceleration, and set them equal to each other. And then you can solve for t. For the Roadrunner, at constant velocity, in other words, 0 acceleration, we can use the simpler equation, x final equals x original plus average velocity times time. And because x original we're taking as the 0 point, we can just write, x original is 0, so that cancels out. We can just write that as x final equals velocity times time. Because again, no acceleration. For Wile E. Coyote, since he is accelerating, we have to use the somewhat more complicated equation of x final equals x original plus v original times time plus 1/2 at squared, which simplifies just to 1/2 at squared because, again, x original is the same for both of them, and we're taking that as the 0 point in space, or distance. Wile E. Coyote starts accelerating from rest because he's hiding behind a bush, and therefore his original velocity is also 0. So that term drops out. So we're left just with 1/2 at squared for Wile E. Coyote. Also notice that you could have used this equation for the Roadrunner as well. It's just that for the Roadrunner, acceleration would be 0. And so 1/2 0 times time squared, that term would drop out. And what you would have left is essentially the same equation that we're actually using. In this case, the equation says original velocity times time. But if there's no acceleration, then the original velocity is the same as the average velocity, and you can use this equation here. Or like I said, you could use this one and just put 0 in for acceleration. So that would work out the same either way. But you cannot use this equation for the coyote because he's accelerating. So you have to have something that involves acceleration. Okay, so for both of them, we just set one equation equal to another to the other, since both of these equations give the final destination or the final position, and we know from above that the final positions have to be equal to each other. Therefore, VT equals 1/2 AT squared. And in order to work that out to solve for T, we've got T on both sides, and we've got other stuff on both sides. So what you're going to have to do is sort of segregate the times on one side of the equation and everything else on the other side of the equation. So let's see, if we divide both sides by 1/2 A, we can get T squared alone. So VT over 1/2 A equals T squared. Now to get T on the other side, we're going to have to divide both sides by T. So dividing this side by T cancels T out, and you divide this side by T. So we have V over 1/2 A equals T squared over T. Well, T squared over T is just T. So there we have it, V over 1/2 A. You might want to make this equation look a little nicer by noting the fact that if you have 1/2 on the bottom, that's the same as multiplying by 2. Or in other words, 1 over 1/2 is 2. So it's actually 2V over A, and that is T. Okay, and that is what we ended up with. Okay, so 2 times the average velocity, that's for the Roadrunner, over Wile E. Coyote's acceleration should equal time. And so when we put those numbers in, the Roadrunner's velocity was 10 meters per second. Wile E. Coyote's acceleration was 4 meters per second squared. So 20 divided by 4 is 5, and it's 5 seconds. It takes 5 seconds for Wile E. Coyote to catch up to the Roadrunner. And for B, for displacement from the start of the chase, well, again, that's the same for both. So you could use either equation of motion in order to get your answer. Just go back to the original equations we had there. Either this one, XF equals VT, or XF equals 1/2 AT squared, and you should get the same answer. Oops, sorry, they're off screen. XF equals VT or XF equals 1/2 AT squared. Since they're at the same spot, the displacement should be the same for both of them. And it should come out the same. And in fact, I worked it out for both of them. Using the equation for the Roadrunner's motion, X equals VT, you get 10 meters per second times 5 seconds. That's 50 meters that they've traveled during that time that the Coyote was chasing the Roadrunner. And using the Coyote's equation of motion, we've got X equals 1/2 AT squared. That's 1/2 4 meters per second squared times 5 seconds squared. So remember to square the 5, and you get 50. So it is the same either way, just like it should be. All right, well, I see we're a little over time for the first video, so I'm going to cut it for a first segment of the video, that is. And so I'm going to cut it there, and we'll pick up where we left off in a moment.